In this video, we're going to talk about binary search algorithms. In our previous video, we talked about sequential search, which is sometimes called linear search. In the sequential search, we begin at the left-hand side of the list or array and compare a key value to each element in the array until either we've exhausted all elements in the array, proving that the item is not in the collection, or until we have found a match for the key value within the collection, at which time we know that it is in the list. Today, we're going to talk about an alternative called binary search. Binary search is another search algorithm, and this one is used specifically when lists are provided in sorted order. So binary search only works in sorted order. Sequential search will work in both sorted and unsorted order. In the examples that we did in the last video, we looked at sequential searching through a list that was not sorted. Let's look at an animation so that we can get an idea for how the binary search algorithm differs from sequential search. In the binary search, or let's think about how we would search through elements if we were given like a big stack of papers. Suppose I had a stack of papers for all 60 students that are part of Computer Science 220 this semester. And suppose that they are already sorted so that they're in alphabetical order. And suppose that I was looking for the paper for somebody with the last name Smith. I could apply the sequential search where I start with the first item in the collection. Maybe that person's last name is Adams, and I compare Smith to Adams, and that's not it. So then I would move to the next element in the collection. Maybe that person has the last name Baker, and I could compare Smith to Baker, and that wouldn't be it. And then I would move to the next element in the collection, and suppose that person's last name was Cooper. I could compare Smith to Cooper, and that's still not it. And I could keep going in that sequential fashion in order to find the person with the last name Smith. I would certainly get there eventually, but it would probably take me a lot of comparisons to reach the matched item if it were in the collection. Probably a more natural way, the approach that you would take if you were in real life looking at a stack of papers like that, is you'd kind of split it somewhere in the middle and say, let's say that the middle item's last name was Miller. We'd look at Miller and Smith and we'd say, you know what, Smith comes after Miller, so I don't have to worry about anything at the first half of the collection. I only need to look at the second half of the collection. And then maybe I'd divide the remainder of that second half of the list in half, and maybe I'd land on a last name like Rogers. So I'd compare Smith to Rogers. Smith is still bigger than Rogers, but that would mean I knew that I didn't have to search anywhere in the M through R zone of the list. I'd only have to look at the portion of the list after Rogers. That's the approach that's used in the binary search algorithm. Let's look at the animation. In this animation, we see that we have a list of 10 items, and we're looking for a key value of 24. Scanning through the list quickly, you can see that there's no 24 in the list, but let's see which items are compared to the 24 using the binary search. So as we begin, the first item that's compared is the item in the center of the list. Just like when we were imagining that we had the stack of papers and we looked at Miller first, rather than starting over at the beginning with Adams. So we compare to the middle item, which is 73 in this collection, and we see that that's not a match for our key value. At this point, because we know the items are in sorted order, it makes absolutely no sense to look for the 24 in the second half of the list. If we know that 24 is less than 73, then there's no sense at looking for that value over here in the right-hand side of the list. We only need to focus our search on this first half of the list. Next, we pick the middle item from this second half of the list, and we're comparing to the value 23, which is in the center position here. 23 is not equal to 24, and we know 24 is bigger than 23, so that means that there's no sense in searching over here to the left of the 23. We know that if the item 24 is in the collection, it's over here between the 23 and the 73 that we searched previously. So again, we divide the list in half. This time we're comparing to this 37. 37 is not equal to 24 either. And then finally, we compare there's no values in between this previously searched 23 and the 37. So at this point, we know that the 24 can't possibly be in the list. We've exhausted the potential positions where that value could be stored. So in this case, we were able to determine that the 24 wasn't in the list, and we made 3 comparisons in order to make that conclusion. Now, we probably would have found that out if we knew that this list was in sorted order and we just started at the beginning comparing with sequential search. We would have compared the 24 to the 11. That's not it. Then compared the 24 to the 23. That's not it. Then compared the 24 to the 37. That's not it. And at that point, we'd know that 24 is less than 37. So if this is in sorted order, the 24 can't possibly be in there. Let's do another example. This time, let's look for a number that would be in the second half of the list. So suppose we're looking for a number like 92. Again, we would start searching in the middle of the list, and we'd compare to this 85. It's in the center position. The 92 that we're looking for is larger, so we only have to search in this second half of the list between this value labeled middle and this value labeled high. We pick the item that's center in that collection. That's this 94. Again, we're looking for the value 92. 92 is not equal to 94. It's less than 94. So we only have to search these center items, the ones in between the values we've already searched. Next, we're going to search the value at position 5, which is this 86. 92 is bigger than 86. So now we only have this one position left to search, the one at position 6. And then finally, we compare to that value and see that it's not equal to that value. It's less than it. There's no items that are in between the one we've already searched through and the one we're currently looking at. So that means we've exhausted all of the positions in the list, and we can conclusively say that 92 is not part of the collection. You can see in this case, we only had to look through 4 items. But if we had gone through sequential search starting over on the left-hand side, it would have taken 1, 2, 3, 4, 5, 6, 7, 8 comparisons or 7 comparisons in order to conclude that the 92 isn't part of the collection. Let's think about how we could translate these ideas into Java code. So I'm going to start with the same starting point that we had written last time with the sequential search. I'm just going to delete the sequential search algorithm out of the middle here. I think I copied and pasted something in here. Okay, so I'm going to, again, delete my searching algorithm and just leave the starting point that we had last time. So in this case, I'm going to make a smaller array so it's easier for us to trace through. I'm going to set the length equal to 5. And I'm going to create a list. Just like last time, I'm going to prompt the user to enter 5 data values into my list. And I need them to enter those 5 values in sorted order. Add that to my input prompt. Then just like last time, I'm going to print out my list so that I can feel confident about the values that are in there. And then finally prompt for my key value, the thing that I'm searching for. So now I want to add in my sequential search algorithm. You might remember that in the animation, we were keeping track of 3 different integer index values. Let's look at the binary search again. The integer values that we're keeping track of were labeled low, middle, and high. And it kept track of the portion of the array that we still need to search. Initially, when we were searching and we were looking at the first value in the array, we wanted to consider all the possible values in there. Then once we compare to the middle item, we decide we're only going to search the lower half or only search the upper half. And when we do that, we adjust the values of low, middle, and high accordingly so that they correctly delimit the portion of the array that needs to be considered. Let's declare those three values in our program. I'm going to declare a low value. That's always going to start at 0 because that's the left-hand side of the array. Also going to declare a high value. That's always the length of the list minus 1. And let's think about that. So suppose our array has 5 elements in it. That means list.length is going to be 5. That means that the indices in that collection are 0, 1, 2, 3, and 4. In other words, the highest index is always the length of the array minus 1. And then finally, I need to create a middle value that I can use to determine where I should search next. Just like in the sequential search algorithm, I'm going to write my algorithm using a while loop, where I tell the computer to keep going while I haven't found the item. And we'll think about how to represent that in just a moment. In the meantime, let's think about how we would calculate the middle value, the value that we want to search initially. So that's always the index low plus the index high divided by 2. And remember that when Java does standard division, if the numerator and denominator are both integer values, as they are in this case, then the answer of this division operator will also be an integer value, which is fantastic because then we can successfully use it to reference the middle of our current collection. Let's write our algorithm so that we have a Boolean value that tells us whether or not we've located the item. So I'm going to make this Boolean value, I'm going to call it found, and I'm going to initialize that to false. And I want to keep going in my loop while the found value is false. Now, once I calculate my middle value, I want to compare the item in my list at that middle position to the key value. If the list at position middle is equal to key, that means we've located the item within the collection. And that means we've found the item. So I'm going to set found to true in that case. If we've located the item, then there's no sense in searching through additional items in the collection. We just want to exit the loop. We have 2 other possible cases to consider. If that item in the middle of the list isn't equal to the key that we're searching for, then perhaps the key is less than the value at the list at index middle. So if the key is less than list at index mid, then I want to update the portion of the array that I searched through on the next iteration. And let's look at that visually. So if I'm comparing to the center item in the collection, let's say that I'm looking for a value like 10, and I'm comparing to the item in the middle of the collection, let's say that's the 46. 10's less than 46, so that means I only have to search the portion of the array over here to the left. When that's true, I want to leave the value of low alone, and I want to update the value of high so that it's 1 less than the current value of middle. So I'm going to change the value of high. I'm going to assign it a new value, mid minus 1. And then our last test case is if the key is bigger than the list at index middle. Oops. In that case, let's look at an example. Suppose that I'm looking for a value like 100, and I'm comparing to the 46. 100 is bigger than 46. So I want to adjust the value of low so that it's 1 bigger than the current middle value so that I only look at these items over here to the right. So I'm going to adjust the value of low so that it's equal to mid plus 1. Once I've broken out of my loop because I found the item, I could print out a message saying whether or not I found it. So if found is now true after this loop completes, then that means that I found the item. When found is still false, that means I didn't find the item. I'll print a message saying that. Awesome. Let's test out our algorithm so far and see if we've forgotten to consider anything. So I'm going to enter 5 values. Remember, I have to put them in increasing order. I'm going to include 1, 3, 40, 70, 90. Whoops. Excellent. And then I'm going to search for a key value. Like, let's search for something that's part of the list. I'm going to look for the number 70. So my algorithm is able to consider the list successfully and identify that 70 is part of the collection. Let's run it again with something that's not part of the list. 1, 3, 20, 40, 70. And let's say that we're looking for a value that's not in there, like 13. You can see that in this case, my program just keeps running and running and running and running, and it never tells me that the value isn't found in the collection. Remember, anytime you're running a program and you're not getting an end result, that is an indication that you have an infinite loop in your program. Let's stop our program so that we can check to see where the infinite loop might be occurring. So we just have this one loop in here that we've written recently. So we know the problem's not with like entering the values or printing the values. Those are fine. It has to be in the algorithm for our binary search. And we added a case where we're going to end the loop because we found the item. But if we don't find the item as we're searching through the collection, then this loop condition will always be true, and it will create the infinite loop. We need to add something in here that says if we run out of items in the collection to search through, also end the loop. And you might remember that in our examples, if we're looking for something, let's say we're looking for the value 60 in this example, we'll search at the middle position, and then we'll rearrange the low and the high so that we're only searching through the half of the remaining list. And then we cut the list in half again if we haven't found the item, which we haven't in this case. 60 is not equal to 65. And now we're searching through just half of the remaining list. Then we're comparing this 60 to 48. It's not a match, so now we're just going to compare to the right-hand portion of the list. And finally, we conclude that 60 is not equal to 58. Watch what happens when I press next. See how the values of low, middle, and high change. So after we've compared to that last element in the list, when we update the values of low, middle, and high, the value of low becomes greater than the value of high. And that's the indicator that tells us that we've exhausted all the possible positions in the list and that we should end the loop. So we also want to add something into our loop condition so that we check to see if the low value is less than or equal to the high value. That means we should keep going. If we ever have a value of low that's bigger than high, that means that the remaining portion of the list to search through is non-existent. And that makes sense, right? At this point in the algorithm, we don't have any remaining portion to search through, and that's represented by the fact that the value of low, the kind of like left-hand boundary of the remainder of the list that we need to search through, is actually larger than the right-hand boundary, the like ending point of the array that we need to search through. Let's run our program one more time and see if we can get that proper behavior when our list does not contain the value that we're looking for. So I'm putting in 5 numbers. Let's search for something that's not in there, like 13. Now that we've added that extra condition into the list, it's able to properly identify the fact that 13 is not part of the list. Let's run through our program one more time. This time, let's use the debugger so that we can see the various values that are compared as we're moving through the collection. So I'm setting a breakpoint here on line 28. That's the line where my binary search algorithm begins. And then I'm going to click the little bug symbol so I can start the debugger. My program's asking me to enter my 5 items. Let's add 1, 3, 30, 50, 60. And then we need to enter a key value. Let's say that we're looking for the value 50. So moving through the collection, you can see the values of low and high as we're beginning. So low is equal to 0 and high is equal to 4. Remember, that represents the fact that we're looking through all of the values in the collection, everything from index 0 through index 4 in our array. Now we're calculating the value of mid for the first time, and it's calculating it at 2, because 0 plus 4 divided by 2 is 2. So we're going to look at the value at position 0, 1, 2 in the collection. We're going to compare the key value that we're looking for to the value 30. And then we know the value 50 is actually bigger than 30. So we're going to execute this else part of the, we're checking through these various if conditions to see which one will get triggered. So far, we checked to see if 50 was equal to 30, and that's not true. Now we're checking to see if 50 is less than 30, the value that's at position 2, and that's also not true. So we're going to trigger this last else here where the key value 50 is bigger than 30, and we're going to update the value of low, and you'll see it change in the bottom pane of the screen so that it becomes equal to the current value of mid, which is 2, plus 1, so the value of low will become 3. So now as we're searching through our collection, we're only looking at the values at indices 3 and 4. Those are the only possible places where the value 50 could be stored. We know that because 50 is bigger than 30 and the list is in sorted order. So this next time through the loop, we're comparing to see if we haven't found the item. That is true. We have not found the item yet. In other words, found is still false. And the value of low is 3, and that's less than the value of high, which is 4. So the whole loop condition is true, and we're going to iterate through the loop another time. So we're going to calculate a new value of mid. Low is currently 3 and high is 4. So we're going to add those together and get 7. 7 divided by 2 is 3 because we're going to truncate the decimal portion of the answer and only store the integer portion. You can see that down here in the debugger where it's showing us the value of mid. So at this point, we're going to look at comparing the key value, that's 50, to the value in the list at position 3, 0, 1, 2, 3. That's the value 50. And 50 is equal to 50, so we're expecting it to say that the found value is true, which in fact it does. And that will cause us to exit the loop the next time around because now the value of found does not match false. So we'll drop out of the loop. We've identified the item, we found it, and now we're going to print out our message saying that the value 50 was found in the list. And you can see that is what prints out in the console output. Remember that you can use the debugger anytime to trace through algorithms. It's a great idea to type in the binary search algorithm on your own and then trace through it using the debugger so that you can see how the values of low, middle, and high change for a particular list. It's also great to kind of reason through this on paper. And so you might want to draw an example array and then trace through it either using the debugger or trace through it using our animation. You can custom input a particular list of values. So you can use like whatever values you want to use for your collection and search for a particular value in that collection. And test your knowledge so that you can see whether you can correctly predict which values are compared in the process of identifying a solution. Let's flip back to our notes because I think there's a couple questions at the end about binary search. Let's talk about those. So in here where it's asking you to trace through the values in the list, that's asking you to identify how the values of low, middle, and high would cause you to compare the key value of 8 to these various items in the collection. So you can trace through that on your own by hand. That would be a great activity. And then use the animation tool or the debugger to trace through it with the computer and see if it gets the same values that you predicted. Here's what I wanted to talk about. So does the binary search always take fewer comparison operations than the sequential search? Think about that with our array algorithm. Need to do like better input here. Let's say I entered all of my values. Okay, perfect. And let's say I'm looking for the key value 1 in this collection. Think how many comparisons that would require if we were using sequential search. It would just require one comparison, right? First time through a sequential search, we compared to the value at index 0, and we immediately find a match. So we would not continue with the search after that point. We'd be able to say definitively, yes, the key value 1 is in the collection. On the other hand, if we were using the binary search, it doesn't look at the first value. It looks at the middle value. And so it would compare the 1 to the 30, then realize that it couldn't possibly be in that back half of the list. It could only possibly be in the first part of the list. And so in this time, it calculated a new value for middle, it happened to be 0, and then compare the key value to the item at that position to locate the 1. So in that case, we compared to 2 different items before we identified the fact that the 1 was in the collection. So it doesn't always take less time than the sequential search. Sometimes in sequential search, you get lucky and the item you're looking for is one of the very first items in the collection, and that allows you to find it very quickly and efficiently. However, overall, if you have large lists and you know that they're in a sorted order, using the binary search allows you to more quickly identify whether or not a particular value is in that collection, because it allows you to compare to fewer items. And comparing to fewer items allows your algorithm to execute more quickly and still give you the correct answer. So for large lists that are in sorted order, most people prefer to do a binary search because it allows you to definitively say whether or not a key value is in a collection very quickly and efficiently.